So yeah, hi everybody. My name is Dmitry Vorobiev. I'm a research scientist at LASP at CU. And today I'll tell you about Sprite and something else that's crazier at the end. But for now, Sprite is the project of PI Brian Fleming. I am the project scientist. I kind of help him build this whole thing. And I'll give you a brief introduction of what it is. So Sprite is NASA's first 12U satellite for astrophysics. It will operate in the far UV. It's going to be about the weight of a large dog. You can see here, it's technically a microsatellite. It's not a nanosatellite. And the Sprite has a dual mission. It will perform an imaging survey of some supernova remnants in the galaxy and in the Magellanic Clouds. But also, it will do a second survey of some more distant galaxies at about redshift 0.15 using its fancy slit. So this is the spectral range we're interested in. Sprite is really sensitive at about 1020 to 1100 angstrom region. And this is driven by the improvements in mirror coatings and detector efficiency that Carlos mentioned. So I won't dwell on that too much. Much of this, of course, has been technology development driven by things like LUVOIR, so we're benefiting from larger mission concepts here. So these improvements are really important and staggering. As Carlos mentioned, the throughput improvement you get by improving a coating, for example, from 67% to 85% is massive after you do a couple of folds. And in the past, UV instruments, far UV instruments, avoided optical complexity because the throughput loss was unacceptable. But now, with better coatings, we can have more complex systems, which leads to much better optical performance, which then leads to much greater sensitivity. So our spectra are spread out over smaller regions of the focal plane to give us better background reduction, less noise, etc. So all of these things kind of work in tandem. Right. So new mirror coatings make Sprite possible. And in the bottom right, you can actually see a mirror coating fixture we have built to coat very large monolithic optics. This is this particular is a 2-inch by 2-inch sample, but it's 3 inches thick. And it's important because you need to deposit these coatings at a high temperature, 250 degrees Celsius, and heating a large piece of glass uniformly has lots of challenges that we're working on. Okay, so the other key thing about Sprite and what makes it as efficient as it is the design of its slit and its spectral performance. So here you can see a simulated observation from Sprite. You can see the full slit in the geocoronal lines. Of course, you see the really bright Lyman alpha line. In particular, there's a lot of scatter. This little square here in the middle of the slit is our 60 arcsecond kind of imaging region where galaxies will go. The rest of the slit is how we'll map nearby supernova remnants using imaging spectroscopy mode. So between the Lyman beta and the Lyman alpha lines from the atmosphere, there is a really faint spectrum, and this is really the signal that we're after. And without a really excellent tight spectra, for example, they don't bow like the spectra from Fuse, which you see on the bottom right, which they have to be this way because they have really just the imaging grading to create a spectrum. And there's only so much you can do to control the shape. So by not having flaring spectra and keeping the background low, we are able to have pretty decent SNR in this far UV region, even for distant galaxies. Another interesting thing that happens with MCPs, as we're going to use an MCP for this, of course, is that the smaller your spacecraft, it seems the smaller is the background on your MCP detector. And Sprite is really small. And so we expect a very low background. for this. This is what Sprite looks like. It has a very large rectangular mirror. Due to advancements in small set technology, all of the bus electronics are shrinking. That means more and more of the spacecraft volume can be taken up by the instrument itself. And you can see that most of Sprite is this big telescope and the detector and the spectrograph behind it. So we are building a custom high voltage power supply for this, which is really exciting to go along with the miniaturized MCPs that were developed, for other planetary and astro missions. I think everybody here is using the same MCP. Right. Oops. Oh, there's sound here. Okay, this is the detector being opened. That sound was terrible, I'm sorry. Okay, this is kind of a summary slide for Sprite. It will be launched in 2022. Most of the components either have been fabricated or are being fabricated now. The telescope is being fabbed right now. It's actually going to be polished soon. We're going to send it to Goddard to be coated. The spectral bandpass is the 100,000 angstrom about region, really optimized at around 103, 106 nanometers. Yeah, so this is a pretty mature instrument at this point. But since this is informal, I thought it would take a minute to tell you about something really insane, which is a mission concept that we call SUMO, the Spectroscopic Ultraviolet Multi-Object Observatory. And it's basically multi-object Sprite. It'll operate in the FUV. There are two flavors, the short end of the FUV and the kind of a longer end of the FUV. The minimum size for this is a 12U, because the spectrograph itself, we just can't fit into a 6U form factor. But its design scales really easily into the larger small set platforms like a 27U or the ESPA ring class satellites. So very roughly, it uses a digital micromirror device, which is an array of tiny mirrors to perform basically slit creation. This is like a microshutter array on the Webb telescope, but these reflect. And this means you can have parallel channels where you can image most of the field with some kind of imaging instrument. Maybe it's a silicon detector, maybe it's an MCP, but also in parallel, your slits are sent through a spectrograph, which is then for SUMO will be recorded with an MCP. This is the most compact version of the instrument, which is similar to Fuse in that the spectrograph is really an imaging grating. So this is done for throughput reasons and also for spatial constraints. So just like Sprite, we're enabled by advances in coatings and detectors, and the multi-object capability is enabled by the use of these devices that I worked on for a while to enable their use in space and in the FUV. And this is just a brief summary of kind of what SUMO could look like. And on the left-hand side here in the shorter wavelengths, you can see the effective area that we expect for different form factors. So starting from the bottom would be a 12U, a 27U, and an ESPA class type instrument, using the protected lithium fluoride coatings for the really short wavelengths with a certain photocathode material for the MCP. But if you're interested in the longer part of this, you can use a more conventional magnesium fluoride coating for your mirrors and something like a more broad bialkali photocathode for an MCP. But you can see that because of the recent advances in these mirrors and detectors, in a pretty small form factor, you're approaching, and outpacing like Galax type performance for a much smaller mission, smaller budget, smaller size, everything. So very quickly, this kind of MOS operates in a standard MOS mode where you pick targets from a field and you get nice unconfused spectra. But you can also perform integral field observations using a special modulation technique that's possible with DMDs, where you will have a true integral field image for any scene, a cube, right? But what's really neat is you can also do weird things, like you can perform slitless spectroscopy, but not of every object in the field. If there are some bright targets you don't want, that would really make really make your spectrum confused, or there's some kind of bright target where the scatter from the grating will really dominate your signal, you can actually choose to delete some of these targets and only perform your slitless spectroscopy on the fields that you're interested in, or the targets you're interested in. And so this is kind of a spooky thing that I think is like spectroscopy of the void, right? You only take spectra of like the stuff where there isn't bright objects. So anyway, I think that's kind of cool. Okay, so I'll just end with the Sprite summary slide here. So that was Sumo.